Hello and welcome back. My name is Dr. Mark Taylor. This is Delaware Tech Physics 111 Lesson 6, Part 2. This is part of the third lesson of Unit 2 on forces and energy, and it's a continuation on the section on forces, Part 3, which includes work and power. So this particular section is considered advanced. You're not required to learn it, but I will tell you the portion on Newton's law of universal gravitation will help you understand one of the labs that involves gravitational force, and believe it or not, it will also help you understand electrostatic force. That's the force between positive and negative charges. Believe it or not, this formula for gravitational force, or the force due to gravity that was worked out by Isaac Newton, is remarkably similar to the formula for electrostatic force. That's the force between positive and negative charges that was worked out by Coulomb. And we'll see that formula when we get to Unit 4. All right, so Newton worked out the law of universal gravitation, and what he found was that the force between any two bodies with mass, that this gravitational force depended on three things. It depended on the mass of each of the two objects that were attracted to one another and the distance between them, specifically the distance between their centers, if you want to be technical about it. So the formula that he worked out is shown here, and it can be written with the big G in the numerator or to the side, so it really doesn't matter which way you write it. But this says that the gravitational force equals G. This is not the same little g that you saw before. That's the 9.8 meters per second squared. This is big G. This is what's known as the universal gravitational constant. It's a very tiny number, 6.674 times 10 to the minus 11. It's a very tiny number, and it is a constant. It has units of Newton meter squared per kilogram squared, and the reason why it has these units is because when you use this in the formula, your final answer of force, of the gravitational force, will be in newtons. And you'll notice capital G, the gravitational constant, is multiplied by both the first mass and the second mass, and that is divided by the distance between the two objects, between the centers of the two objects, squared. It is extremely important to remember that that denominator, that with the distance is squared. And the importance here is that when Newton was working out the relationship between this gravitational force and the masses and the gravitational force and the distance, he found certain relationships based on the fact that the two masses are in the numerator and the distance is in the denominator, and it is squared. And what he noticed was the following proportionalities. Gravitational force is directly proportional to mass 1. What does that mean? That means if you double mass 1, you'll double the gravitational force. If you triple mass 1, you'll triple the gravitational force. If you divide mass 1 by 10, you will divide the gravitational force by 10. Whatever you do to mass 1, whatever you multiply or divide by mass 1, the same thing will happen to the force that results. And all of this is true for mass 2 as well. So if the force is directly proportional to both mass 1 and to mass 2, we can also say that the force is directly proportional to mass 1 times mass 2. So if I doubled mass 1 and I tripled mass 2, well, doubling mass 1 would double the force. And then if I tripled mass 2, that would triple that number. So tripling a double results in increasing the force sixfold. So you have the proportionality to both masses. And then the other proportionality, which is probably the most famous one of all, is the relationship between the gravitational force and the distance. The gravitational force is inversely proportional. First of all, that means that when one goes up, the other goes down. When one goes down, the other goes up. But it's not that the force is inversely proportional to the distance. It's inversely proportional to the distance squared. And this is actually referred to as the inverse square law. And while this might seem a little odd, the inverse square law tells us that distance has a big effect on the gravitational force, and this same inverse square law not only affects gravitational force, but it also affects electrostatic force between positive and negative charges, negative and negative, positive and positive, and it also affects magnetic force between the north and south poles of magnets. Each of these forces are strongly affected by distance. They are inversely proportional to the distance squared. So one example of this inverse square law would be, what happens if you have a gravitational force between two objects and you tripled the distance between those objects? In other words, you've increased the r, the distance between the two masses, threefold. So if the r is increased threefold, you have to ask yourself, what happens to the force? Well, the force of gravity, the inverse part of the inverse square law, tells you that an increase in distance will result in a decrease in force. The squared part tells you how much that decrease is. So if I am increasing the distance threefold, that means I am decreasing the force 3 squared fold, or 9-fold. So a tripling of the distance, a threefold increase of the distance, results in a 9-fold decrease in force, a much greater change in force, and it's in the opposite direction. And that makes sense if you think about, if I'm pulling two bodies away from each other, the force between them will be less. And in fact, it will be a lot less. And if I bring them closer together, the opposite will happen. Let's say I had the situation where I bring them closer together. I decrease the distance to only 1/5 of what it used to be. In other words, I've dropped the distance 5-fold. I made it 1/5 of what it used to be. Well, what will happen is the force of gravity will increase. Okay, they're inverse relationship, inversely proportional, but not just directly inversely proportional. They're inverse to the square of the distance. So I have to take the distance, what I've done to the distance, which is decreased it 5-fold, and I square the 5-fold. That means it's 25-fold increase in the force. And that's a gigantic increase in force. So bringing them close together has a huge effect at increasing the force in this case. All right, so the universal law of gravity almost always works. And in fact, the reason why it's called universal is because it works not only when you're studying the Earth and its gravitational force with the sun, the Earth and the moon, or any of the other moons and planets, etc., big objects, but it also works to study small objects, an apple dropping from a tree, the famous story of Newton. It probably never happened, but the story is that Newton was looking at an apple dropping. It didn't actually fall on his head. If this did happen, he saw an apple dropping and realized that the force that causes an apple to fall to the ground is exactly the same force that keeps the Earth tethered to the sun. They're connected by this gravitational force. And he realized both forces were the same. This is why it's called universal force. The reason why I say it's almost always works, there are very special conditions when there's extremely high gravity or extremely high velocity where objects are moving close to the speed of light. Then you have to tweak this formula, and Einstein worked out how to do that in 1905 with his theory of general relativity, which is the current working model for modern physics to study gravity. But this is the first stop in understanding that, using Newton's formula for universal gravitation first. If you were to take a more advanced physics course, they might get into Einstein's general relativity. One of the things that bothered Isaac Newton about gravity, when he studied other forces like friction or a pulling force or a pushing force or the normal force, all of these things involved contact between at least two different objects. But gravitational force doesn't require contact. It's a force that acts at a distance, and in fact, Newton referred to it as a spooky action at a distance, and he couldn't understand how gravity could possibly work if the moon and the earth aren't touching, if the earth and the sun aren't touching. How do you transfer this gravitational force? And this was actually worked out by Einstein as well in his general relativity paper. But that's a whole nother discussion. But the point to realize here is we refer to gravitational force, or the force due to gravity, as a type of field force, not a contact force, a field force. So there's this imaginary field around every object that has mass, and the denser the field, the stronger the gravitational force from that mass. And we'll discuss that a little bit later. But gravitational force relies on these gravitational fields that all objects with mass have, no matter how small or how big. It could be a star or a whole galaxy or a whole cluster of galaxies, or it could be something as small as a proton or an electron. In theory, every object with mass has gravity and will attract every other object with mass due to that gravitational force. All right, so you already learned that gravitational force, when it pertains to weight, in other words, the gravitational force of an object or a person close to Earth or standing on Earth, we already talked that you have this simple formula. Force of gravity or weight equals mass times little g. And that formula works really well as long as you're very close to the Earth. But when any objects have a gravitational force, and it doesn't have to be even the Earth, and it doesn't have to be an object on the Earth, any two objects, if you want to determine the force, the more general equation for doing that is Newton's law of universal gravitation, this formula that I just showed you. Now you might be wondering, where does this formula come from if this is the real formula? Well, here's the deal. If you assume there's some object on the Earth, and you can think of that object, could be a person, could be an apple, could be a box you drop, a ball you drop from a building, anything close to the Earth, that we'll call that mass 2. That'll be our second mass. Our first mass is going to be the mass of the Earth. So we're talking about the mass of the Earth as the first mass, and the mass of some object as the second mass. And if we plug those into this formula, we have capital G, that big that little constant, but with the big letter, times the two masses, mass of the Earth and mass of the object. And then we divide it by the distance. Well, what's the distance between anything sitting on the Earth? Well, the distance between anything sitting on the Earth, and remember I said the distance is always between the centers of those objects. Well, you have to go to the center of the Earth. So the center of the Earth to the object, and we're going to assume the object is very, very small relative to the Earth. This is obviously not drawn to scale. The distance between those essentially is the radius of the Earth. That's the distance between you and the center of the Earth. That's the radius. And don't forget to square this number. Well, when you actually use the radius of the Earth, which is about 6 million meters or 6,000 kilometers, and you use the mass of the Earth, which is about 6 times 10 to the 24, that's 6 with 24 zeros, kilograms. When you put those two numbers into the formula, and you just separate the mass of the object. So I just pulled the mass of the object to the side of the formula and just wanted to calculate everything else. Well, when I put those numbers into this formula, something really interesting happens. I put the capital G in here, I put the mass of the Earth in here, and I put the distance between you and the center of the Earth, which is the radius of the Earth, and of course that's squared. I plug that in, and lo and behold, look what I get. I get that all of that grouping of numbers is equal to 9.8 meters per second squared. So what you find is that the formula of weight equals m times g is just a special case of the real gravitational formula when one of the masses is the Earth. In other words, we're attracted to the Earth, so we have to use the Earth's size and we have to use the Earth's mass in the formula, and we get a g. If you were to ever see a g for some other planet or some other moon or some other star, that g would have to use the mass of that object and the radius of that object to get its little g. But the capital G, that's a universal constant. That is always going to be the same number. That's that 6.674 times 10 to the minus 11 number with units of Newton meters squared per kilogram squared to make everything work out so that your force ends up being in newtons, just like all forces. So let's look at some universal gravitational force problems. Number 1, consider a 70 kilogram student standing on the surface of the Earth. The mass of the Earth is 5.972 times 10 to the 24 kilograms. There it is written in floating point decimal. And the radius of the Earth, that is the distance between the student and the center of the Earth, is 6.371 times 10 to the 6 meters. That's about 6.3 million meters. All right. Using Newton's law of universal gravitation, what is the force of gravity that the Earth pulls on the student? Well, let's write out our formula. We'll remind ourselves that the formula is that the F sub g equals the gravitation constant times the mass of the two objects, and one of these is going to be the Earth, and one of these is going to be the student, and that's going to be divided by the distance between the two, and that's going to be squared. Well, the distance between the two is the radius, so we can actually start plugging in our values directly. We know that G is 6.674 times 10 to the minus 11 Newton meters squared per kilogram squared, and that's times the mass of the Earth, which is 5.972 times 10 to the 24. That's a very big number of kilograms, times the mass of the student, which is only 70 kilograms. And now we're going to divide all that by the distance between that student and the Earth. So it's really between the center of the student and the center of the Earth. Well, the student's tiny compared to the Earth, so the distance to the center of the Earth is the radius of the Earth, so that's 6.371 times 10 to the 6 meters, and we square that number. And then I strongly recommend, if you don't already know how to use scientific notation on your calculator, please learn. Just ask a tutor or instructor. They all will know how to use the calculator scientific notation. We're going to put these numbers into our calculator, and we're going to end up with a final value of 687. Now, what are the units here? Well, we know we should have units of Newton. Well, let's take a look. We have Newton meter squared per kilogram squared times kilogram, and then divided by meters, but those meters are going to be squared. So the meters squared will cancel the meters squared. The kilogram and the kilogram will cancel the kilograms squared, and the only unit left will be Newton. So moving to part B, question is, with what force does the student pull the Earth? All right, well, we've just learned the gravitational force between the Earth and the student is 687 newtons. Well, Newton's third law of motion is very clear on this. If one object acts on another object with a certain force, the second object will act on the first object with exactly the same force, just in the opposite direction. So if the Earth is pulling on the student with a force of 687 newtons, then the student is pulling on the Earth with exactly the same force of 687 newtons. But of course, that reaction force is pointing straight up. All right, part C, use the simple equation for weight, F sub g, to calculate the same student's weight on Earth. Well, our simple equation is m times g. We have 70 kilograms for the student, and we have about 9.8 meters per second squared. And when we've been using this, 9.8 meters per second squared is an approximation, and that's because the gravity is slightly different everywhere at every point along the surface of the Earth. So keep that number in mind with a grain of salt as far as how accurate it is. When we multiply these together, we actually get 686 Newton, which is essentially the same value. All right, looking at the next questions, we have a couple multiple choice questions that relate to the proportionalities and inverse proportionalities of Newton's universal law of gravitation. So I'm just going to write the formula over here on the side, and hopefully this will make these proportionalities a little bit clearer. So the force of gravitation, or the gravitational force, is equal to a constant, capital G, times the mass of the two objects, mass 1 and mass 2, and that's divided by the distance between the two squared. If you want to use D for distance, that's fine. We tend to use R for distance, and you'll notice R is squared. All right, question number 2 says, according to Newton, tripling the mass of one of the interacting objects. So let's say mass 1 was increased by 3-fold. Results in a gravitational force that will, well, if we increase this number 3 times, our final number is going to be 3 times bigger. So this will also be increased 3 times. So our gravitational force will also increase 3-fold. And that is because the force of gravity, or the gravitational force, is directly proportional to mass 1. Whatever you multiply or divide by mass 1, that's what you multiply or divide to get your force. The same is true for mass 2. All right, question number 3. According to Newton, tripling both of two interacting objects results in a gravitational force that, so we're tripling the mass of both of them. So we've got mass 1 that's increasing 3 times, and we've got mass 2 that's also increasing 3 times. Well, this will result in the force going up 3-fold, and so will this. Well, if you were to triple something, and then triple it again, that's a ninefold increase. And if you're wondering why it's ninefold, okay, let's make it as dollars. If you had $1 and I said you can triple that, you would say, oh, I've got $3. And then I'd say, okay, you can triple it again. I think most of us would realize, oh, now you have $9. And it's the same thing with increasing the force, because the force is directly proportional to each mass as well as the product of the mass 1 times mass 2. But you can just do them separately. You triple the number, then you triple it again. So you're increasing it ninefold. And the last problem here of these multiple choice, the last question says, if you're increasing the distance between the objects fourfold, that is, the objects used to be a certain distance, and now you're spreading them apart so that distance is 4 times further apart. All right, what happens to the force? Well, the force is inversely related to that distance, because this is in the denominator. The distance squared is in the denominator. And because it's squared, if we want to know what happens to the force, we have to find out what happens to the distance and square what happens to it. Well, what happens to it is its fourfold increase. So that means the inverse part of this rule tells it's going to be a decrease, and the square part of this rule tells it's 4 squared. So that means it's a 16-fold decrease in force. In other words, if you spread out these objects, make them 4 times further away, the force between them will go down 16-fold. And this is quite a dramatic change in gravitational force. So let's just review what we've learned here about gravitational law proportionalities. So we have the formula up here to remind you, and gravitational force is directly proportional to each mass. It's directly proportional to mass 1. It's also directly proportional to mass 2. In these examples right here, you can see that if I increase one mass threefold, the force will increase threefold. If I increase both masses threefold, in other words, I triple the mass of each of them, well, that will triple the force, and then it will triple the force again, which results in a ninefold increase in force. Now, this is to be compared with gravitational force being inversely proportional to the distance squared. If the distance is increased, the force will decrease. If the distance is decreased, the force will increase. In other words, you bring the objects closer together, the force will increase. You pull them apart, the force will decrease. But how much it decreases depends on how much you've changed the distance, and then you square that change. For example, increasing the distance threefold, and you triple the distance, you make them much further apart. That will result in not a threefold decrease in force, but a 3 squared fold decrease in force, or ninefold. 3 times 3 is 9. Decreasing the distance, in other words, I'm moving them much closer. So for the example here, decreasing the distance fivefold, that means I'm cutting the distance down to 1/5 of what it used to be. I'm bringing them much closer together. That will increase the force, but not by fivefold, by 5 squared fold, or 25-fold. It's a giant increase in force or decrease in force when you change the distance. So putting these two concepts together here, what happens when the gravitational force of the first mass is increased twofold? So you've got one mass that's increased twofold, you've got a second mass that's increased fourfold, and the distance is increased twofold. Now you might look at this and go, there's no way I know how to solve this. Well, you do each one separately and then just multiply or divide the results. Increasing the first mass twofold will double the force. So that's a twofold increase in force. You're going to double it. If you increase the second mass fourfold, you're now going to quadruple it. So you've doubled it and then you quadruple that. Well, that's eightfold so far. You've increased it eightfold. You doubled it and then you quadrupled your double amount. 4 times 2 is 8. And then finally, you increase the distance twofold. Well, increasing the distance twofold decreases the force, not by twofold, but by 2 squared fold, and that's fourfold. So instead of multiplying by 4, you are dividing by 4. Well, 8 divided by 4 is simply twofold now. So your final result is a twofold increase in force. And you can use the money analogy if this is giving you trouble. Imagine you start with $1. First, you have to multiply it by 2. That's what we found in the first part of this. We multiply it by 2. We have $2. Then we multiply it by 4. We have $8. And then you have to divide that value by 4 in order to give you $2. And $2 relative to what you started with is a twofold increase.